Okay, so this class marks sort of the start of a shift, another shift in the course from basic statistical models to more advanced machine learning techniques. And I think up until this point in the course, the topics have been fairly balanced in terms of, the expertise involving data processing, basic statistics, machine learning, hypothesis testing, this kind of stuff. And now I admit for this next 5 lectures, we're going to forego all illusions of fairness, and we're going to talk about machine learning. And we're doing that because I work in machine learning, and I want to give you, doing that, I feel like I can give you good intros to a lot of these topics. But also it's because, when you get a job as a data scientist, I think more and more, they are kind of expecting knowledge in machine learning. And so maybe not all these algorithms, but at least some of these algorithms you will probably use in your career as a data scientist. You might get asked about them in interviews, and so it's going to be worth knowing the basics here. I am also actually changing things up a little bit. I might do this more so as we go forward. I'll try to keep a rough schedule the same, but I'm changing things up a little bit. I was going to try, I don't know why I envisioned this in the schedule originally. I was going to try to cover both kernels and boosting today, but that's a little bit crazy, I think. So I'm just going to cover decision trees and boosting today. Even that's actually 2 topics that deserve their own lecture in and of themselves. But hopefully, I think we can get through that pretty well. We'll see if we get through it all. So a couple quick announcements. As always, homework 4 is due tonight, as I'm sure everyone knows. After talking about how easy it was at length to write an SVM, I found out from Eric that I actually had a misplaced parenthesis in my SVM code. That would be on page 26 in the slides. The formulas were all correct, but I put a negative sign outside the parentheses instead of inside. And so that actually negated the regularization term. Instead of adding it, you were subtracting it, which is not what you want to do. For small regularization, it doesn't actually have an effect, but for larger, it will have an effect. So if you're copying the code directly, I've updated now, but sorry about that. It goes to show that, there is value in using libraries, even when you know how the algorithm works, just because it's very easy to make a little typo and not realize it for a long time. And I am obviously very guilty of that myself. We're going to try, I shouldn't say we will try to send feedback for the tutorial midway reports by tomorrow. This is going to be very brief feedback. This is probably, this is a quick scan of your submission. We aren't going to read it twice. We're going to read it in detail, of course, for the final grading, but we want to give some feedback, but this is going to be a quick glance over. That's going to be the extent of it. And we're going to try to send that out by tomorrow night. And then for those people doing a tutorial on k-means, they're a little bit more disadvantaged now because the original tutorial was due on Monday, but we're covering k-means on Monday, so they have to submit by Monday, even though the tutorial for everyone else is due on Wednesday. So sorry to those people, but there's not too much option there. OK, any questions?
Is PCA covered on Monday as well?
PCA will cover on Monday, yeah. I think I said that to the k-means and PCA folks. I think I sent that announcement out. But yes, both are covered. Oh, I realized I didn't, hang on one second. I didn't insert my sections into this. All right. OK, so this lecture is going to cover the following things. We're going to talk about decision trees, first of all, what they are and what how they act as a machine learning algorithm. These are one of the oldest algorithms, actually, for machine learning. They're not the oldest. Things like the perceptron was around, which is sort of a simple linear classifier. And then, of course, least squares, logistic regression have been around for much longer before the term came about. But decision trees were one of the first kind of algorithms considered in the framework of machine learning. And despite being one of the first, they're actually, and despite also not performing necessarily that well in a lot of problems, they have a lot of value in their ability to explain the logic behind the decisions they're making. So they are useful in and of themselves. We'll talk about them when we'll talk about training. Classification, mainly decision trees, though we'll also talk a little bit about regression trees as well. And then I'll talk about boosting. Boosting, on the other hand, is a technique that uses decision trees, but is actually one of the most powerful machine learning, off-the-shelf machine learning techniques that we have. And so it's kind of ubiquitous in a data science toolbox, and so it's very, very good to know about. And then we'll finally, if we get to it, cover some examples. Okay, so let's talk about decision trees. Who here has seen decision trees before in any form? Okay, so maybe half, a little more, 2/3 maybe. All right, decision trees and boosting, as I said, are some of the most sort of common algorithms in data science. And so they're very important to kind of get some experience with and get some familiarity with, even if you probably, unlike say an SVM, you probably won't write your own, say, boosting classifier. It isn't actually that hard. I think there's this perception that's actually quite hard. It's actually not. But it's maybe 100 lines of code instead of 5 lines of code. And it's 100 kind of dense lines of code. So I won't make you do that. Maybe 50 actually is. But if you write very dense code, you can maybe do it in 50. But scikit-learn, I think, does it in about 3,000. So there's room there to get as complex as you want to. But sort of amazingly, in some sense, this technique that combines boosting, which is a technique that combines multiple decision trees together, is actually really, I would say, kind of one of the most ubiquitous state-of-the-art machine learning algorithms. So neural networks are getting a lot of press right now, and certainly a lot of interest academically. But if you look at, for example, who wins the most Kaggle contests, which I don't think is a great example. I've mentioned my issues with Kaggle before, but as a sort of a metric of pure kind of what's the easiest machine learning algorithm to apply to X some unknown data set, it is instructive, I think, that boosting very, very frequently wins these competitions. It's incredibly common for some boosting technique to win, and even common for the top 5 entries to all be just different takes on boosting algorithms. So it is an amazingly effective algorithm, and it has some huge advantages, and it works well, importantly, without too much tuning. So there isn't all that much you have to do to make these things work well. And decision trees, while themselves not as powerful, are actually, in some sense, coming back in fashion a little bit. The reason for that is that decision trees, unlike most machine learning algorithms, are very easily interpreted by a human. So we can look at this classifier and very easily see why it's making the decisions that it makes. This is in contrast to something like a deep neural network, where the decision process is very opaque to a human. It looks like a complete black box that you have no insight into. So decision trees themselves are actually, while they don't quite have the accuracy of other techniques, they themselves are actually really still, and I think will continue to play a big role in machine learning, especially when we talk about interacting with machine learning algorithms. All right, so let's talk about decision trees. As I said, they're one of the first machine learning algorithms, and they're actually very simple and they're very intuitive, which is why they're so appealing in many ways. So the idea here is, suppose we have some input x here, and here I'm considering x. I guess x could be as big as you want, but say x has at least 2 features. And we'll assume here that they're real valued features, though we'll quickly also consider the case where there may be binary features as well. And the idea of a decision tree is you branch down certain thresholds on certain values in this feature vector. So I might, in this example, compare x1, my first feature, and see if it's greater than less. Oops, I wrote 0 there. Greater than 2. I might as well be consistent. Greater or less than 2. If it is not, and the left arrow here means in all cases no, it's not. The right arrow means yes, it is. You make another choice and say now branch on the value of x2, right? And eventually, when you reach a leaf, so now I'm going to say that x2 is greater than or equal to 2, no, or yes. And at some point, you reach a leaf in this tree, and at the leaves in the tree are actual predictions. So I'm going to call this just h0, and that would be, say, or h1, I guess I use the h1, and that would be, say, I make the prediction 0.1. And we're not going to worry about what that prediction signifies. It's just a hypothesis function, so it just outputs some number, right? They could be probabilities, they could be real estimates in a regression task, etc. Okay, so that's the model of a decision tree. And the way to think about what this is doing graphically is that this tree is providing a partitioning of the input space. Okay? And it's partitioning it specifically with axis-aligned boundaries. And this is really important because this is what differentiates decision trees from, say, linear classifiers. Right? So a linear classifier also partitions the input space into a positive region and a negative region, right? So, we had some data points in logistic regression, for example, and we would say that, this place here is positive and this place here is negative. Oh, I wrote almost positive there again. This place here is negative. But decision trees, because they split on individual features here, right? It's not saying x1 plus x2 is greater than equal to something. It's just saying x1 itself is greater than equal to something. The thing that looks like in this space is that looks like a boundary that's aligned with one of the axes. Right? So if I'm splitting on x1, this being x1, this being x2, this would be a split, the visual representation of a split on x1. Right? And of course, unlike just pure linear classifiers, decision trees can have many further subdivisions. So a way to think about it is sort of as a picture like this, where the decision tree recursively partitions the space into multiple different regions. So for instance, everyone can see that, yeah. So this first node corresponds to this line in the space here that says everything that is above, say, 2, falls into one category. Everything's below 2 falls in another category. If we follow down the first branch in that tree, then the left branch, that branch there corresponds to this slice in the space. And notice that this slice only spans across the area that was already partitioned by its parent node, right? So we don't cut across the whole space here. You just cut across the portion of the space that you're already in. But this partitions the x2 variable to being greater than or less than 2. And then you finally reach a leaf in the tree, which corresponds to one of these whole regions of space that has been partitioned by this decision tree. And the key point here is that the hypothesis value for a tree in one of those regions is just a constant. So every point in the space that falls within this region receives the same value for its prediction. And that is a decision tree. Any questions on that? Fairly intuitive, hopefully, but actually a very powerful representation. Okay, so let's talk about how we train decision trees now. This is sort of the hypothesis class you can think of. In fact, we'll formally define it as that in a second. But let's talk about how we actually build these things to fit some data. And we're first going to talk about classification, though I'll have one slide in the end. So that means that the target variable we're trying to predict is a 0, or is a discrete random variable, is a discrete variable. Y's are discrete, though we can also generalize it to y also being continuous for regression tasks. Now, remember, and I think this is actually a key part, because oftentimes decision trees are treated very differently from the rest of machine learning algorithms. They're somehow in a class of their own, and they're not formulated in terms of hypothesis classes and loss functions and optimization, but they are doing the exact same thing. So I'm going to run down decision trees in the same framework we talked about before, as we're going to talk about them specifying a hypothesis class. We already saw that, actually. That's the hypothesis class, is axis-aligned partitionments. But we're going to talk about them as specifying a hypothesis function, a loss function, right? So how do we measure how good a tree is? And then finally, how do we actually minimize this loss function? Where here, theta is going to refer to kind of just the parameters of the function, but it's going to refer, theta is kind of going to capture, all the descriptors of the tree itself, which I'll mention in a second. So how do we find a tree? How do we build a tree that minimizes our loss function? So it's the exact same protocol in some way as every other machine learning algorithm. We just make, notably different choices here. And we'll see what kind of effect that has on the resulting algorithm. Okay, so let's start off. First of all, what's the hypothesis function? It's just decision trees, right? We already covered that, actually. The hypothesis function for a decision tree is itself a decision tree. And that sounds weird. This is one of these problems where, again, the terminology is bad here. Decision tree can refer to the actual hypothesis class itself of the tree. But more often in machine learning, it actually refers to the entire algorithm by which we build the tree and actually minimize some loss function. So again, like with everything else, you have to be a little bit careful here about our notation. We've been very bad at that as a field. But what we are doing here is we are basically going to talk about the hypothesis function being these axis-aligned partitionings of the state space. That is the hypothesis function of a decision tree. And again, I'm going to use theta here as kind of shorthand for all the parameters of that tree. So that includes things like the nodes that you branch on, the structure of the tree, the predictions of the leaf nodes. All that is kind of being wrapped up in theta. I could define, theta 1 equals the index of the variable you first split on, and theta 2 is the comparison point, and then theta, you do some sort of ordering of the nodes hierarchically. But I'm going to forego all that and just sort of say, look, theta defines the structure of and values in the tree here. And I'm not going to worry. I'm going to kind of use that a little bit informally and just say what we're doing when we find theta, we'll find the parameters of the tree, is we're actually going to be determining the structure and the predictions of that tree. Okay, so what next is the loss function? And this is where I think oftentimes presentation of decision trees kind of they don't do justice to this notion of loss, which is really crucial to decision trees as well. So I'm going to first assume for now, I'll talk about the regression case in a second, but I'm going to assume for now that our output space is binary valued. So this is a classification task, a two-class classification task. And actually, to make it a little bit more like other notation, I'm not here going to use -1 and +1. I'm going to use 0 and 1. That's just for convenience. The loss function here is more along the lines of a probabilistic loss function. So I'm going to use the notation more from my probability lecture rather than the machine learning lecture before. So it's a minor thing. Of course, they're equivalent, right? It doesn't matter if you call it 0, 1 or -1, 1. But just the notation here makes it a little bit easier to do that. OK, so the loss function is actually really easy to, I shouldn't have erased that. Oh, whatever. The loss function here is actually very easy to describe. It's just the loss of a Bernoulli random variable. So the probability of y given h theta of x, that is the output of my decision tree. And the only restriction here is that's going to be constant over each individual partitioning of the state space, right? That's going to be the same over that region. But the law, or the probability that I observe some y, I'm going to define this just as this hypothesis to the y times 1 minus the hypothesis to the 1 minus y. And if you remember, this is exactly the same function we use for Bernoulli random variables. So remember when we had a Bernoulli random variable, we just called this is sort of a trick we played, right? Where we can kind of say, if y is 0, then this thing is 1. And so you have this as your probability. If y is 1, then this is 0. And so you have just this as your probability here. And so in both cases, basically, either h of theta or 1 minus h of theta denotes the probability of the observed data either being 0 or 1. So this is actually just the same likelihood we had for a Bernoulli random variable. Does that make sense to everyone? Is that reasonable? OK. And our loss function under this model is just the typical log probability loss, or negative log probability. So our loss that we're going to define between our hypothesis and our output is just equal to the negative log probability of y given our hypothesis. This is exactly the same thing we did for logistic regression for least squares if you have a probabilistic interpretation. So it's just the standard way of defining a loss function in terms of probabilities. So I think that, and by the way, I should also write that this is also, if we just expand this, this is equal just to y h theta of x, yes, plus 1, or the negative, sorry, the loss is a negative probability, so it's negative there. Minus 1 minus y log 1 minus h beta of x. Okay, so that's our loss function for a decision tree. We want to construct a tree that minimizes this function on the training data over all possible trees. That's the goal that we have set out. So now, the key question, of course, is how do we minimize this loss function over our parameters, in other words, over the space of all possible decision trees. And now we hit a little bit of a snag, because unlike our linear models before, or even unlike more complex models we'll talk about like neural networks, we can't take gradients with respect to our parameters theta. Right? We can't actually do that. These theta parameters encode structural things about a tree, right? They encode, which index do you use? That's not something you can differentiate. You can't sort of have you can't take, make small modifications to a tree and have it a little bit like, this node being the first one, but a little bit like this other node being the first one. It doesn't really work. At the same time, so that means there's no gradients. We can't do things like gradient descent to optimize these things. At the same time, there are a huge number of potential trees that there can be. So if you actually look at the number of possible ways you can structure a decision tree, so the number of possible partitionings of the state space, you can enumerate it. It is finite. It is finite assuming that, say, your input data even is binary valued. So assume that our inputs actually are even 0 or 1 as well as our output. The number of possible decision trees actually ends up being 2 to the 2 to the n, right? So for 7 features, that means 10 to the 38 possible trees. There's no way to search over all these possible trees, is the point here. You cannot do exhaustive search. It's even harder than doing exponential search. It's double the exponential search, right? So it just does not work to try to enumerate all these trees and evaluate which one's the best. So here's what we're going to do instead. We're going to use approximate greedy optimization to iteratively minimize that loss function. All right, and that's the key idea of what we're going to do with decision trees and how we're going to train them. And in particular, we're going to build the tree one node at a time. All right, so let's consider what I mean by that. And this is going to be sort of actually the key points of this lecture. I do see now why they put that thing there, but it's still annoying. But it doesn't float up now. You can still see the diagram. Okay, so we're going to consider a single leaf in a tree. And so what that corresponds to, really, if you go back a few slides here, that corresponds to a single region of our input space, which, by the way, could be the entire space. So if we haven't built a tree yet, if we just have one node effectively, which would just contain every example, that would be a leaf in a trivial tree. But we're going to consider one leaf. Okay, and in this one leaf, so I'm going to consider some leaf in my tree. So I'll just draw like that. And in this leaf, there are some number of examples, which I'll write as script x, that fall into that leaf. And really, script x is going to be some subset of all, xi and yi, right? Could be the whole thing. Could be just some subset. It's all the examples from my training set that fall into that partition. So now a very basic question is, if I want to find the best hypothesis for this region, what should that be? And I'm going to assume now that my outputs, as before, are in 0 or 1. And my loss that I want to minimize is this probability of the data given my hypothesis function. Okay? Well, this is actually, it's sort of obvious, right? What you do, the thing you should predict is exactly the same as our estimate for a Bernoulli random variable. Remember, all we're trying to do here really is just minimize the loss we suffer when we make our prediction. I'm going to also, for convenience here, call x positive to be all the subset of this that have y equal to 1. And similarly, x negative will be the subset that have y equal 0. And so it's somewhat obvious, right? But really, h should just be the number of positive examples we have divided by the number of of total examples we have, right? So in that, if you want to know the best prediction that will minimize that loss function, you just predict the average of how many positive examples there are. And by the way, this is the exact same derivation as the maximum likelihood estimate for a Bernoulli random variable, right? In other words, what we're trying to do is really trying to minimize over my one prediction I can make. So remember, I have to make the same prediction for every point at this node. The sum over all x and y in this guy. Did I write it that way? Yeah. Though actually, it doesn't really matter what the x's are because I can't make a different prediction based upon their features here. I have to make the same prediction for all of them. So minimizing the loss between my hypothesis and y, which is equal to this loss, remember, was from 2 slides ago, 3 slides ago, is just this thing here. And so that is just going to be equal to, if you sort of write it out, equals negative number of, actually the average loss, if I divide this thing by the total number of samples just for convenience, it's just going to be this thing. It's going to be the loss of this times the log h plus this number of negative examples where we suffer loss of log of 1 minus h. All right, and when I take derivatives with respect to h here, sum equal to 0, I get this. Everyone kind of remembers how that worked, right? Okay, so that gives me the, again, remarkable result, of course, that if I'm trying to estimate, if I'm trying to minimize my loss I suffer from a single where I just have some set proportion of positive and negative examples, I should predict the portion of positive examples. That should be my hypothesis in that region of the space that minimizes my loss function. And, kind of importantly, this, if I plug in, of course, this thing here, right, that just achieves loss. So this is now, my hypothesis I predict is this value, but if I plug in this hypothesis to my loss function, the loss I actually suffer because of these examples here is just equal to, and I'm going to kind of overload notation here and call L also the total loss I suffer, but that's going to be equal to just negative h log h minus 1 minus h log 1 minus h. Okay, and that's just really, this is 1 minus h, this is h. I'm just plugging that in, plugging in my solution to what I get. Yeah?
We able to consider spaces where we, in each space we assign the label which is the same probability as the probability of the positive class.
Yeah. And
then I look for the best possible space, which minimizes number classification. So
that was sort of it's hard to repeat that whole question. But yes, here we are talking about assume that we have a fixed space. So assume we have some fixed partitioning that just has some number of examples in it. We are now going to talk about how do I actually divide up the space to make the total number of, to also minimize the loss I suffer here. I'm just stating maybe the obvious fact here that if I have a set space with a set number of positive and negative examples, and I'm doing this binary classification with this probabilistic loss function, my prediction should be the proportion of positive examples. That's all I'm saying so far. So now the real question is, how do I split? How do I choose whether or not I should split this node? And if I do want to split it, how do I choose what variable do I split it on? Remember, decision trees can split the space with axis-aligned boundaries on any variable, right? So I could split this node based upon some feature xj, or x5, or I could split it based upon feature x6. How do I know which split is the best one to make? All right, and this is actually kind of the key element of decision. Oh shoot, this is where this gets annoying here. Let's see how high I can push this up. Oh, man, that was the easy way to get it out, that little thing there. All right, well, you can see all of them now.
Professor hates you.
Well, I actually see why he did it now, he or she did it, but I did not mean to undo it just then. I meant to try to get that screen up. Okay, but let's see how we go about doing this. Okay, so now we have our space, our set of sample points x. That could be the whole system. That could be the whole space if we're just starting off with the fresh tree, or it could be some node later down in the tree. We don't really care. I'll talk about exactly why, how we handle both situations in a second. But the idea is we're going to pick some xj, and I'm going to split my space now into the set of points where xj equals 0 and xj equals 1. And for the time being, I'm actually going to assume that xi is actually in 0, 1 to the n. So I'm actually going to assume that my features are also all binary. Very soon I'll talk about the case where the features themselves are numerical. But we can actually handle both those cases pretty easily, but it's a little bit more clear if I start off with the case where the split is kind of obvious, because what you're going to do when you split on a feature is you have to move all that are equal to 0 in one side of the tree, all that are equal to 1 in the other side of the tree. Eventually we're going to modify this to do splits by greater than or less than comparisons, but this is sort of what we're doing for now. Okay, so this region gets all the examples where this feature xj is equal to 0. And I'm going to call this set now x0. This set is x1. I'm going to not worry about xj. I'm just assuming that j is fixed through all this discussion, at least on this slide. Okay, and we'll also define like x0, positive and negative 0, this similar as we did before. Oh, sorry. X positive and negative. That's the positive examples that are in the x0 set, the negative examples that are in the x0 set. Okay, so if we do this, suppose we are going to split on this feature xj. Okay, in that case, we are going to have two new hypotheses that now encompass these new regions of the space. One for this region, we're going to come up with some new hypothesis to classify all those examples according to h0, and one for this region, classifying all those according to h1. And of course, this is just going to be the number of examples in x0 that are positive over the total number of examples in x0. And this is going to be equal, so this is h1 there. This is going to be equal to the total number of examples that are in x1 positive over the total number of examples in x1. Hopefully you can read that, but it's just exactly on this slide here, so not too important if you can't. Right, so if I split, what I will do is I will split my data set that is in this partition into two new partitions. And in each one, I'm going to, of course, try to minimize their loss. And what that will do is that will predict a constant value of h0 in this region and a constant value of h1 in that region. Right, and now here's the key point. Each of these new leaves will also suffer some loss. Right? So there's going to be a loss that I suffer, according to my loss function, from this node. That's going to be, I'll call it L0, and that's going to be equal to h, just negative h0 log h0 minus 1 minus h0 log 1 minus h0. That's this one. And then over here, I have L1, which is going to be the same thing, but just with H1, negative H1 log H1 minus 1 minus H1 log 1 minus H1. Right, so I suffer some new loss according to each of those. Right? And remember, the original loss I suffered in my original leaf was that. And so there's the key point. If I decide to split this node here on this variable xj, I no longer suffer this loss L, because that is no longer sort of a constant prediction over that time. So I don't suffer my loss L, but I instead suffer loss L0 and L1. So basically, if I think about my total loss, which I'll just write capital L, this is like the sum of losses for the entire data set, this is going to be updated to be equal to L1 plus L2 minus L. Or sorry, I should write this a little more clearly. My total loss is going to be equal to the old loss plus the new loss I suffer minus the old loss I suffered at that node. Okay. That is the change in my overall loss function if I decide to split this partition on that feature. And this term here, the delta in the loss, is called information gain. It's actually negative information gain. The information gain is the alternative. Actually, wait. Yeah, information gain is the other one of that. So you're. Wait, no. Yes, the negative is information gain. Now, if you've seen decision tree before, you've probably seen this written out, essentially more information gain written out in terms of entropy. That's all true. So these terms also are entropy terms. So you can actually write them in terms of entropy. But this is, I think, a much more rational way to look at it. All they're really doing is they're saying, I'm going to pick the split that makes the biggest difference in my loss function. Right? So the decision tree learning algorithm is just the following. For all the nodes that are leaves, and for all the features of the tree, I'm going to evaluate what is my change in loss function when if I were to split that node on this feature. So I'm going to evaluate that for all the leaf nodes and all the features. I'm going to choose to split the one that causes the biggest decrease in my loss. And that's why information gain is the criteria you use to pick the node. I mean, people just define it differently, but that's all that's going on. I'm just taking the biggest step I can to minimize the loss as most I can, because I know that I can't actually search over the set of all trees. So I'm just going to find, what's the best split I could do to make the biggest difference. Yeah?
Will a split always make your loss go down, or can it?
It's a good question. What do people think? Who thinks it can make your loss go up?
I haven't done the math.
Okay. Who thinks it can only make your loss go down? I guess I should say keep it the same or go down. You could always say the same, right? Because if you have, if all your features are in this node, xj is always equal to 0, then this will have no values in it, and this will have the exact same values as the parent, and so it won't make a difference. Okay, so I will claim that it will always decrease or stay the same. And the reason for this is that this space, the space of having two hypotheses there, is always a greater space than having just one hypothesis to classify everything. So I know that this space is actually minimizing my loss actually minimizing my loss over this expanded set of hypotheses, which include my original hypothesis of just having one, right? Because I can always just pick them to be equal to 0, to be the same, rather. That's a very hand-wavy argument, but that is why, with no math actually, that is why you can never increase your loss by a split. You can sometimes make no difference. For example, as I said before, if all the examples here have xj equal to 0, you're actually getting no examples here, so everything's going to still fall into that category, so you still have the same loss. Even if that's not the case, you can actually have a situation where you split something, but the breakdown is the same in the later two nodes, so you get no advantage by splitting on that feature. So it can stay the same, but it can never increase. Yeah? Yeah, so if there's no samples, you can split as much as you want. It won't do a whole lot. What will actually happen in this thing is you'll never get there, because to create a leaf with no samples means that the loss here that you suffer in this set here will be exactly the same as the loss here. In other words, there's 0 information gain. In other words, you don't decrease your loss at all, and so it isn't really that useful. I should be clear that actually information, so this thing, just to be perfectly clear, because I sort of muddled my sentences, this thing is actually is a negative information gain. The amount you decreased your loss, and therefore it's actually, this will be a negative quantity because your loss will go down, and so the negation of that is actually the gain, just to be clear. Out of curiosity, if people have seen this energy before, did anyone describe information gain like this, or did they just describe what information gain was in terms of entropy and then use it? Yeah, I never understood that, because it made no sense to me why you would pick entropy as something, but it's just minimizing a loss function, like any other machine learning algorithm is. So I mean, maybe it's more opaque this way, I don't know, but it seems much more intuitive to me this way.
Isn't entropy kind of like the loss?
It is, but it's never defined that way. It's just defined as some way of, maybe we want to split on entropy because it decreases our uncertainty or something like that. But of course, I mean, this term is the entropy, and this term is the conditional entropy, if you want to know. But it's just loss functions. Okay. Yeah, it's all the same equations you get at the end, though. I never figured out why they use information gain until I saw it like this. So hopefully, if you've seen it both ways, this will give you a little bit more intuition as well. Or maybe not. Maybe it'll just be complex and it'll just be confusing. We'll see. OK, so a few more points, a few quick points, actually. And that deals with which I'm going to cover very quickly, but they're actually, of course, very important in practice. And I want to just highlight them mainly because I want to try to convince you that they are not that hard to handle. So the first thing is that what if the xj's, what if some feature is not binary, but it's actually discrete, or it's actually continuous? So discrete's actually just not that hard. You just instead of, if it's just discrete, it has one of 3 possible values, you just split on all 3 values and compute the loss here. But if it's actually continuous, things are a little bit trickier. But fortunately, they're not that tricky. So what you do in that case is if xj is continuous, then what we're actually doing, now I'll pull this one back down. If xj is continuous, in that case what we are doing is we want to pick some threshold where everything that is lower than that threshold for xj we put in one bucket, everything is greater than we put in another bucket. We could do like multiple thresholds as well, but that actually gets a little bit complex. So usually our split rule is something like this. It says, xj less than or equal to some threshold c. If so, we go in this way. Otherwise, we go this way. That's the normal rule. And the way we do that is actually the exact same procedure as before. All we're going to do differently is we're going to search over kind of all possible values that threshold could take on. And we don't have to do a continuous search, fortunately. We don't have to do, look over an infinite number of values. We can look over only the number of values that actually are, that we have data points. So the idea is very simple. We're going to take our feature xj, and we're going to sort our data points based upon that feature. So we're going to line up all our data points. So notice here, my superscripts are not just 1, 2, 3, etc. They're actually I1, I2, I3. So the idea here is that xj I1 is less than xj I2, which is less than xj I3, etc. So I'm plotting the value of the jth coordinate for all those data points, right? So I have a line, a bunch of data points. They each have labels, so they can either be positive or negative. I guess blue or red here. And I want to find what should my threshold be such that I minimize my loss. And the idea here is, again, very simple. The only choices of threshold I have are the only ones that really matter are the threshold in between this point, in between these 2 points, in between these 2 points, etc. Right? Every other threshold will actually not split either not split it or be the same as one of these in terms of my loss, because it doesn't matter if I split based upon here or here. I get the same loss in the resulting partition. So all I'm going to do is I'm just going to take all of these possible splits, i.e. the number of data points I have, and just evaluate my information gain on each of these. So I'm going to consider this split. I'm going to consider this set as my x0, and this whole set as x1. And I'm going to evaluate information gain. Then I'm going to move it over 1, make this set be x0, and this set be x1, evaluate information gain. And you actually can do this kind of efficiently. All you have to do, and this is sort of just an aside, it isn't m times more work here, actually. It just requires 1 pass over the data. Because all you do is just keep a running total, a running sum of how many negative examples and how many positive examples I've seen on each side of my threshold. And those are all the only numbers I need to compute information gain, right? This loss function is just based upon the number of examples of each class in each different bucket. So I just compute a running sum, compute all my information gains, and then pick the one with the highest information gain, or i.e. the one that decreases the loss function the most. So that's how you handle continuous features. There are also some other things you can do. So if that is too much work, so if you really cannot do a complete linear pass over your whole data, say you can't even fit your data into memory at one time, it might not be a good idea to do this. You can also do things like random sampling. So it's actually pretty common just to randomly sample some subset of data, do this on a random subset, and then pick that, right? If you have a big enough sample of data, that can work pretty well. Now, one other point, which I think I don't actually have this later, which I want to make here, which is one reason why these things work so well, is that one nice thing about this model is that the actual values of the xj's don't matter. All that matters in picking these thresholds, of course, is their sorted order. And this is sort of a really subtle but key point. So if xj0 or I1, if this is equal to negative 10 to the 8, right? And these are all like 1, 2, 3. Linear models have a really hard time with features like that. And distances have a hard time too. You maybe try to normalize your features, but then they're dominated by this huge value here. So you have to substitute in other values, somehow normalize the data. Part of the reason why decision trees, and in particular decision trees with boosting algorithms, work so well is that they actually don't. There's no. Doesn't matter at all what these values actually are, right? Because if this is the value 10 to the negative 8, 1, 2, 3, it's the exact. I get the exact same classifier as if this thing had value 0, and the sorted order was the same. So they are, in some sense, insensitive. They're very insensitive to the actual magnitudes of the input data. And this is actually one of the reasons why they work so well in practice. Because oftentimes you do have data that's somehow very heavily skewed. You don't really want to spend the time to try to transform it in a way that normalizes the data correctly. And so you can't do that, or you don't want to do that. And so you just apply a decision tree, and it just kind of works. Yeah? So no, you can't really do binary search that easily, because you have it in sorted order, but you the information gain does not necessarily decrease or increase monotonically. So there's going to be, so the information gain here might look something like, here, 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 like this, right? And like that. So you actually don't know how that's going to, I mean, it can't be arbitrary actually, but it can increase and decrease and then re-increase, etc. So you can't just do a binary search there. You still have to do a linear pass over the whole data. So you sort it, and the typical way this is done, by the way, is you first sort it, which takes n log n time, or m log m time anyway, if you have m examples. And then in each split, do a linear search over the data. Because you have to evaluate all of them if you're going to do an exact split.
Is that really, so every time I have one split right, there will be some point which will be added, taken out of the positive example or.
Yeah. So you update your counts of positive and negative examples essentially as you do a move across this data, and you just keep track of these counts as you go.
Threshold exists. Let's say, if the threshold exists, then at some point in time, I would have everything, all one kind of examples on one side.
Well, I mean, they might be interspersed, right? There's nowhere you can go. I mean, I guess the first one you can have all of one kind, but then that's not all the other. They can be interspersed here. And the problem is they're sorted by their x value, not their y value. And the y values are what you're using to keep that track of that running sum. So you actually have to do a search over it. It's actually worth going through the implementation once if you want to get more details about how this actually works in practice. Okay, the other nice thing about yes.
For example, with this example, we have minus 10 to the 8 and like
Yeah.
small features. So at this point, the threshold doesn't matter. But then if we evaluate our algorithm on the test set, then it will matter.
Yeah. So usually you pick yeah. So that's correct. The threshold does not matter, and you can pick something in the middle here, and maybe that's bad. It won't matter though if you have just a few examples that are really with really large negative values, right? And you pick a threshold that's not on that side, then it won't matter. You're right that yes, at test time, it will matter the threshold you pick. Oftentimes, maybe you pick the one that's closer to the mean of the numbers or something like that to make it a little bit nicer. But regardless, it's much easier than trying to retransform your data based upon some other transformation that's much harder to do. Yeah.
So you could also potentially split the data into like 3 or 4.
Yeah. So the question was about splitting the data into 3 or 4 parts. So with discrete multivariate attributes, that makes perfect sense, right? You do just pick all possible values of the feature and then have 3 different buckets instead of 2. With searches like this, it's a little trickier because then now you have to search over 2 possible thresholds, right? Now you have to search over one with this here, and then the second one has to range over all these things. And then you move this one forward, and the second one ranges over all these things, right? So it's substantially more complex. It will raise like a polynomial. The complexity will substantially increase if you try to do that with continuous features, so no one does that. Okay, I have one last slide now on regression trees, which is actually important because we're going to use them when we talk about boosting in a second. But regression trees are exactly the same. The only difference now is that the y's, instead of being binary, are real valued, as they are in our regression task. And therefore also, the hypothesis function, instead of being just between 0 and 1, is also itself going to be real valued. And our loss function we use, instead of being this probabilistic loss, is just going to be the squared loss, right? So our loss between, this is now real value trees, our loss between our hypothesis, again, a constant hypothesis in some region, and a output is just going to be equal to the squared error between those two. And what that means is that if I have some set of nodes in X, I would just take my hypothesis, instead of this thing, there's no notion of positive and negative anymore, it would just now be the mean of the y values in that region, right? Because to minimize the sum of squared losses with a single constant, you just take that constant to be equal to the mean. You can do the median too if you wanted to have like minimize an L1 loss. It would actually be taking the median then, but those all the mean is much more common there. And it suffers a loss equal to the sum of all y's minus their mean squared. In other words, actually that's just their variance, the sample variance. So that's one way of characterizing the losses you suffer. And just like before, you just pick the split that minimizes the loss you get from these two things. So this equation, where was it, is exactly the same. It's not called information gain anymore, but it just generalizes just as well. The exact same algorithm works, where these are now squared losses. They're actually the variance of the data you have in this region, minus the variance you had in your original region. So that's, again, the loss view, I think, gives a nice way of extending this to from the discrete case to the continuous case with actually changing nothing about the notation. It's all exactly the same. I'm just changing my loss function. Yeah? Yeah, so before h, we had y being 0 or 1. And in some sense, our loss we suffered was this probability of observing the data under the assumption that it was generated according to some probability h. Here, h is just a number. And remember, we still have, going back to here, we have some region of the state space. I'm saying that h in that region is a constant number. I have a bunch of data points in that region, and I want to predict some number that minimizes the mean squared error between those data points and that number. And that value for h should just be the mean of all those data points in that partition. To be clear, the mean of the y values of those data points in that partition. Okay, so now let's talk about, in the time we have left, let's talk about boosting. Boosting, as I said, is kind of an amazing algorithm. It's amazing that something that combines decision trees and some kind of fancy math ends up being by far, one of the best off-the-shelf, quick, easy-to-apply machine learning algorithms. It's kind of, sort of brings everything kind of full circle. That we're back to using decision trees after they went out of fashion for a while. Okay, so the idea of boosting and is really based upon something called ensemble methods. And the idea of ensemble methods, and in particular ensemble tree methods in this case, are that we're going to try to overcome some of the disadvantages of a single model class by just using multiple models within that class. So instead of a single tree making our predictions, we're going to take multiple trees and somehow average their predictions. And there are a lot of things you can do. There's a lot of ways you can do this. Probably the most simple, the one that I probably should talk about, but don't because boosting is so useful and is actually often works better. The simpler one is something called random forests, which essentially just use multiple random samples from the data to build many trees and then combine these results. That's all I'll say because I know some people are doing their projects on a tutorial on random forests, and they were not on my list of things to talk about, so people can talk about that. But the other common way of building multiple tree combining multiple tree models is a technique called boosting. And boosting actually refers to a lot of different things. So boosting developed as and boosting kind of is one of these areas that really, I think, though it has made some transition to statistics in recent years, it did come out of the machine learning community. And in fact, it came out of the theoretical machine learning community. It started out as kind of a theoretical algorithm to improve the performance of what are called weak learners. So just very high level here, what the basic idea was that if you have some weak learner, they're called, that can get slightly better than random chance on any data set, you can combine multiple things together and average them together to get as good performance as you want. So basically the idea was that being able to generally perform a little bit better than chance is actually all you need to perform as well as you want. That, of course, is a very theoretical idea because most classifiers will not guarantee that you can perform a little bit better than chance after a certain point, right? At a certain point, they will just perform like chance. So, you know, this was a very interesting theoretical idea, but at least initially it didn't seem obvious how practical it was. And then after and that happens around the early 90s. There was a guy named Rob Shapiro had a sort of I think one of the highest cited PhD theses in all of computer science on a kind of theoretical view of boosting. Now, after some initial success in theory, also Rob Shapiro and the co-author, Yoav Frund, wrote a paper on a much more practical method for boosting. This is called AdaBoost. I'm just kind of rambling here for a little while about the history, so this is not, you know, in the slides, but if you're curious. So this is 1995. They published a paper called about this algorithm called AdaBoost. And this algorithm was a little bit different than what I'm going to talk about today, but the core ideas were the same, even if it had a very different interpretation. But this then actually was a very practical boosting algorithm and really drove boosting to be, along with kernel machines and support vector machines, one of kind of the main classes of algorithms considered in the mid-90s in machine learning. So it really rocketed these methods to prominence from an empirical standpoint. And the point I want to make here is that there are many, many different interpretations. This is a simple process, but there are many different interpretations of what boosting is really doing and how they're really combining their models. Unlike random forest, where it's pretty obvious what's happening, boosting is actually not at all obvious what the right interpretation is. So I'm going to present one view of boosting, and this is called a technique called gradient boosting. It's also referred to as gradient boosted regression trees, which has one particular way of viewing boosting. And I like it because it ties in very nicely to minimizing loss functions. But it is by no means the only one. And it isn't even the simplest one, I should say. I'm giving you kind of the one that usually, but again, I should also say that if you go look at those Kaggle contests, it is almost always some version of gradient boosted decision trees that actually wins the contest. So, sorry, gradient boosted regression trees that actually wins those contests. So it seems to work incredibly well in practice, and it has very nice ties to optimization. So that's why I'm describing this view of boosting as opposed to many other potential views. OK, so let me start off now by stepping back a little bit. And this is going to be actually interesting how we do this. We're going to come at gradient boosting with trees in a very, very roundabout way. So let me discuss how we're going to do this. I'm going to start off by talking about gradient descent, where I'm taking gradients with respect to predictions themselves. All right, so what do I mean by this? I promise you we'll get back to trees in a little while, but it will actually only be at the very end that we get back to trees. So if I have some loss function, and again, this is now, we're back to core machine learning here. This could be any loss function, any classification or regression task, doesn't matter. All the same. I just have my canonical machine learning problem, but I'm going to think about it a little bit differently, right? I have my sum of losses. So I have sum from I equals 1 to m of my loss between my prediction on example I and my actual example I. And this is the thing I want to minimize, right? Where normally in machine learning, what I said was this prediction is equal to some hypothesis we generated on, based upon some parameters. That was sort of my canonical formulation. But I'm not going to think about a little bit more generally and say, suppose I could actually modify these predictions in any way possible. I can modify them however I want, my predictions. How would I modify them? Well, you could probably just set them to be equal to your output, right? That would be nice. But if we didn't want to go the whole way, we can also take a small gradient step in the predictions to make them a little bit closer to the actuals, or in other words, to just sort of minimize this loss a little bit. All right, so I'm going to consider this gradient, the gradient with respect to my prediction of the loss of my prediction and my example. Now, key point here, there is no reason to believe that I can actually find a hypothesis function that is able to adjust my predictions in that manner. Right? I'm just saying if we could do anything we want, if we had no constraints on our hypothesis function, maybe we want one that takes a small adjustment of all our parameters in this direction. So we basically would set, our predictions for all of them to be equal to the old prediction minus some alpha times this thing. Right? That would be a reasonable way to modify predictions if we had no constraint on how much we could modify them. And in fact, these gradients are actually easier to compute than our old gradients. We can compute them very easily. For logistic loss, for example, it's just this. Basically, all that happens is you don't have to differentiate again through your hypothesis function. You just differentiate directly with respect to your prediction. So, for example, for the squared error, this is just equal to the prediction minus that. That's the gradient with respect to that's the derivative with respect to the prediction of the squared error. Similarly, for logistic loss, that's actually very similar to what I had for the gradient of logistic regression. It just does not have like a theta or an xi in there. We don't worry about that. We just worry about directly modifying the predictions themselves. Okay, so now I'm going to do the interesting thing here. And I'll put up this slide in a second, but here's what I'm going to do. I'm going to take these gradients, right? These gradients with respect to every prediction I make. So I'll erase this update here. But I'm going to take these gradients. So the derivative with respect to, oops, I should actually have a I here. So this is the kind of the way that I want to adjust all my different predictions here. Right? I'm going to do this for all I. I'm going to call this a new vector, actually. I think I use gi here. And so g could be a vector of all my predictions. Sorry, all my gradients with respect to my predictions. What I'm going to do now, these are all real value numbers, remember? So g, which is maybe a vector of all those things, would be a vector in Rm, because all of them are going to be real valued derivatives. What I'm going to do is I'm going to fit a regression tree on the data set xi, gi for all my data points. So I'm going to build a new regression task where the goal of this regression task is to predict these gradients. Why do I do that? Well, I can't actually adjust all of these themselves. I need some mapping from my input to know how to adjust my outputs. But what I'm going to do is I'm going to use a decision tree as the mapping from my input space to how I want to adjust those gradients. So here's the algorithm. Here's the gradient boosting algorithm. The idea is we're going to perform something like gradient descent on this actual loss function here. But we can't actually perform exact gradient descent because there's no real mapping between the x's and our predictions here. Right? So what I'm going to do is I'm going to approximate these gradients using a decision tree that predicts what the gradient should be from the input. So it's a crazy idea, and this works amazingly well. So here's the algorithm. I start, I don't know, maybe I'll just, how much time do I have actually? 10 minutes, okay. All right, so I start, I've given a data set, a number of total trees to generate. That also, by the way, equals the number of steps to take in gradient descent. A loss function and a step size. Again, remember, the loss here is regardless, it does not have to do with the tree at all. The tree is always a regression tree because we're using it to approximate gradients. So even if we have a classification task, these are still called gradient boosted regression trees because the trees we build are trying to approximate a continuous gradient. So anyway, I set all my yi's to be initially equal to 0. So I'm going to predict 0 for everything. Maybe you could also predict like a constant number if you wanted to start at a little bit better place. But it doesn't really matter. Now I'm going to repeat for t equals 1 to t. That's the number of trees I'm going to generate. In other words, the number of gradient steps I'm going to take. And I'm going to set this g, these targets, to be equal to the derivative, or the partial derivative with respect to the y hat I of my loss of on the prediction itself. Okay? Then I'm going to train a hypothesis, which is going to be equal to, won't write train regression tree there, I'll just write like RT, regression tree, that is built on the data set xi and these gradient targets gi. So that's going to be, remember now, it's going to be the output of this thing. So h of all of xi is going to be approximately equal to gi. And so I'm going to update my predictions according to that approximate gradients. So I'm going to set them all equal to yi is going to be equal to yi minus alpha times ht of xi. That's an approximation of the gradient, and that's how I actually adjust my output, just like gradient descent, like an approximate version of gradient descent. So that's gradient boosting. That's how you train it. When I want to make a prediction now, and this is sort of the interesting point where it gets really kind of crazy. When I want to make a new prediction now, what I'm effectively doing, what I do is I take my new example, new example x, and I just compute all the trees. And these will kind of be like all the gradients, right? So I'm talking about my prediction, I. The first thing that'll just be equal to h1 of that x, right? What I'm kind of doing is I'm kind of like simulating gradient descent without actually knowing the true targets. I'm using kind of my trees to predict what the gradients would likely be on some new example. And then I modify it, right, to be equal to y hat, sorry, this should be actually alpha, negative alpha. Let me just write that down. Well, actually, let me just say this. I'll just let it be equal to 0. And then I would repeat this thing t times. I set it to be equal to this minus alpha times ht x. This is sort of kind of like what the gradient of the loss would be if I knew what the actual output is. I can't actually compute the true gradient because I don't know the actual output. For a new example, I don't know its corresponding y. I can't compute that loss, but I can approximate those gradients with my regression trees. And so in other words, this would go from t equals 1 to t. In other words, our final prediction actually is just going to be equal to y hat equals the sum, equals actually negative alpha times the sum over all t, is 1 to t, of ht of x. In other words, it is the combination of a bunch of regression tree predictions that predict the gradients. So this is I'm still fascinated by this algorithm. It seems so interesting to me that what we're effectively doing in some sense is we're kind of simulating what we would do with gradient descent if we stepped through this process of optimizing our loss, where we're approximating our gradients by regression trees instead of computing them exactly because we don't actually know the true output. Now there are some modifications here. So it turns out that fitting these trees is relatively slow. So you don't all actually have a question. So this is a new example. You can evaluate the tree on that example. You can sum them up, those predictions, and that's your prediction. And the process this is emulating, it is as if you actually were computing the gradient. I mean, you would like, right, to sort of, you would like this to be, this thing here, to be equal to the derivative with respect to our prediction of y hat and y, right? But this thing, we don't know y. That's the whole point. We don't know the true output, so we can't just make our prediction like the output. So instead, we're approximating this using our trees, which is exactly what they were trained on. These trees were trained exactly to approximate the gradient at the teeth step of gradient descent. So this is what boosting is doing. So we're still minimizing. So the question is, are we training gradients to move towards the actual prediction or not? We're still minimizing the loss function. So we're training gradients to minimize this loss function. We're just taking loss gradients directly in our prediction space rather than in our parameter space. Or we're trying to approximate the predictions directly in our prediction space instead of in our parameter space. Now, of course, what we still have effectively parameters here. Our parameters are just the tree parameters. That's sort of what we're really doing. But we are approximating kind of this process of gradient descent, and then we're carrying it out kind of in simulation for, you can think of it that way, for a new example where we actually don't know the true gradient. So again, there's a few things you need to do to modify this to make this a little more practical. This step here of fitting a regression tree is slow. I mean, it's not that slow. You can play tricks to make it fast, but it's still kind of slow. And so you actually want to spend a little more time trying to find a good step size here. So rather than just picking the step size that immediately a fixed step size like you would in gradient descent, you actually spend some time to try to do like a line search to find the best step size, or even do more. You can even do fancier optimization to think about what would decrease my loss, what step size would decrease my loss the most out of all step sizes. You can do that. You can also actually have a different step size, not just for different from alpha, but you actually can also tune your step size differently at the different leaves of the tree. So that's a little bit detailed. It isn't too important. But basically, what you can do is you can do fancier things that actually help you make bigger reductions in your loss, you actually care about, this loss, than you would if you just take a simple gradient step. And here you probably do want to use a library. So some very common ones are scikit-learn has a reasonable implementation of gradient-boosted decision trees, regression trees. Saying that. XGBoost is another very popular library that's much faster. So if you want to do it on a larger data set, definitely use XGBoost. Don't use scikit-learn. Though scikit-learn is nice because it's the exact same interface as everything else. I guess I might as well just show a couple quick examples here. This is scikit-learn code to fit a gradient-boosted regression tree or a decision tree. And the nice thing, of course, as with all scikit-learn, is exactly the same notation you're all used to for turning any other classifier. The thing you want to sort of be a little bit familiar with, though, is the parameters as normal for these things. So, for example, by default, decision trees actually is a different splitting, essentially a different loss function called the Gini criterion instead of this thing. And I think the entropy one or the information gain one, i.e. loss reduction under a probabilistic model, is a better one. It's sort of a more intuitive one, so I typically use that. You can set things like the max depth of your tree. You can also set things like how you prune nodes. For gradient boosting, you actually can control all the same properties of the regression trees themselves, but in addition, you also have to specify the loss. For some reason, they call logistic loss deviance. I don't know why they do that. not elsewhere, but they call it their deviance. You can also minimize an exponential loss. This is all for classification. For regression, you can minimize a squared loss, or you can minimize like the absolute loss, or other alternatives as well. You can specify n estimators is t there. It's the number of trees you form, and max depth is the maximum depth of the tree. And you can check the notes yourselves, but essentially these are two examples of what they look like on this classifier. On this cancer prediction task we talked about before. Here's a decision tree, and here's a gradient boosted tree. It does some weird things, you'll notice here. Like it puts this line here across the space, which doesn't actually affect prediction at all, because doesn't, there's no points in that line, but it might seem a little bit odd. What I'll say again, reiterate, is that this algorithm works incredibly well on a huge number of tasks, and because it inherits the same properties of decision trees, like the resistance to weird outliers in the data, it often does it with very little tuning. So if I were to pick 3 algorithms to run as a data scientist on most tasks, I would first run linear regression or logistic regression, then use RBF features, and then use gradient boosted regression trees. Now, of course, in the meantime, you want to be sort of analyzing what you're getting right, what you're getting wrong, but we'll talk about that more in some later lectures. So a very, very useful algorithm, and also very cool that this combination seems to work so well. OK, see everyone next time.